tipping points is a framing that I'm sure, as we all know, is very commonly used in the media, it's commonly used in popular parlance, and perhaps because of that, it's something that we hear a lot of questions about, it's something that I personally have received a lot of questions about, and it's something that we know there is a lot of interest in. And the term tipping point is sort of generally used to imply large-scale, abrupt, damaging, irreversible change. But beyond that, having had a little bit of a conversation prior to this session, it's actually not that easy to define what is and what is not a tipping point. For example, as opposed to something that we might describe as a threshold. So earlier this year, a paper was published by David McKay and colleagues, which used the definition that you can see up here on this slide for climate tipping points. And as the paper highlights, there are a number of elements that feed into this that are discussed in more detail in this paper, and also feed into other definitions of tipping points. And some of these elements do bring a little bit of complexity along with them. So for example, how we define abruptness. The IPCC in the past have defined abrupt change as something that happens over a few decades or less. But others have defined it differently. For example, it's been defined before as something where the impact occurs faster than the cause. In this paper, it's defined as something taking place at a rate that's defined by the climate system or subsystem. So the takeaway here is that what is and is not a tipping point is actually an interesting question, but perhaps not a simple question. And the answer is likely to be kind of a little bit dependent on the context, and that's something I think we'll be digging into in this session. I also want to highlight that tipping points as a phrase is often used, at least in the media, alongside other phrases, phrases like on the edge or on the brink. And arguably, this framing is not the most helpful, and maybe it's even problematic. So I say that because if we're on the edge of a tipping point, does that mean that if we cross that edge, then there is a less urgent need for action? Or that we're in some way too late? What does this mean? And who is it that we are describing as being on that edge? We know from discussions that we've had here in this pavilion and elsewhere at COP that for many communities, both within the Arctic, for example living on permafrost systems, and across the world, that already we're seeing substantial, even devastating impacts of climate change, something that we perhaps would not describe as being on the brink. So with that in mind, in this session we're hoping to answer some of those questions that we hear about tipping points, and perhaps move together towards a more productive framing of this broader idea of thresholds and irreversibility. And so without taking up any more time, I'd like to introduce our first speaker, Gustav Hugelius, who is the Vice Director of the Berlin Center of Climate Research. Thank you, Gustav.
Thank you very much for that introduction, and thanks for coming to listen to our sessions, where we try to give some nuance or discussion around the concept of tipping points. And I'm going to start with a really broad-scale overview of the permafrost carbon feedback and tipping points, based on previous research, some of my own research, and some synthesis, and also doing some IPCC work. So far, this is the picture that we're seeing and that we're projecting into the future. Every ton of CO2 has added linearly to global warming if we start in the pre-industrial moving forward. The graph you're seeing here is from the recent Working Group 1 report of the IPCC AR6. You see cumulative CO2 emissions since 1850 on the x-axis and global warming on the y-axis. And at least leading up to 2050, this relationship is pretty linear. There's some divergence between the different SSPs, but not much. And of course, the concern, as when we're discussing tipping points, is that instead of a linear future, we would be moving into something like this, with rapid irreversible acceleration of emission due to other sort of natural feedbacks in the system. this is just a crude hand-drawn line. This is not anything exact, but this is the notion that we're going to be discussing, whether this is what we're moving into. And to sort of frame this discussion, it's really important to think about, I think, the sort of the role of the natural feedbacks and the natural systems in the whole climate change context. This graph, I want to illustrate Earth's natural sinks and how these change depending on different societal pathways or different emission pathways. You've probably all heard that land and oceans together are taking up roughly half of the CO2 that we emit. So for every two molecules, they take up one. And they've been doing us this favor since the start of the pre-industrial. Now what we're seeing, and this is based on a couple of model runs into the future, is that these sinks are shifting and changing, and some of them are starting to saturate or perhaps weaken a little bit as we move further along. And if you look at the far right, you can see the grey fraction of emissions that end up staying in the atmosphere in high emission scenarios is much higher than if you look to the far left, where ocean and land are actually able to absorb 70% of the emitted CO2 emissions. And this is because the sinks are saturating and because of other behaviors. And tipping points, of course, could play a role here in making this trend even more exacerbated, where tipping points that are not currently in the climate model. Just remember that this is based on climate model. If we think of feedbacks that are not in the models, making the sinks even weaker, then this could be an even more dire picture. But so this is sort of the context of what we're talking about, and we're zooming in on the permafrost carbon tipping point. And what that permafrost carbon tipping point, or the accelerating permafrost carbon feedback, I should say, is doing is essentially making the land sink smaller. It's already part of the permafrost system is part of the land sink. As permafrost is emitting more and more, the land sink is becoming weaker and weaker, and in the high northern latitude, that sink might even reverse. So the land section sink of this will get smaller if we have emissions that are higher than what the models predict. So we're talking about this in the context, I think, of this recent paper, that recent review of global and regional climate-driven tipping points in the Earth system. I'm not going to go through all of them, but this map is from this paper. The different colors illustrate different thresholds that were identified or discussed at least in this paper. And we're zooming in on the one that's called boreal permafrost, or boreal permafrost collapse, which of course includes both Arctic and boreal. They lump the whole northern boreal region into one for this paper. And then there are all of these other tipping points that we're not touching upon today. Perhaps a little bit people think of us talking about the boreal forest expansion, I guess, in the context of fire feedbacks. So they have the boreal permafrost tipping point labeled as with the threshold above 4 degrees in this case. We'll get back to that a little bit later. I want to talk a little bit about feedbacks in general, because a positive or a negative feedback is a self-reinforcing mechanism in the climate system. So that emissions either trigger processes that make the climate cooler or stronger. So it's self-reinforcing in feedback, which is not self-perpetuating, as in the case of the definition we prefer for tipping points. This is from the IPCC again, and it shows the feedbacks that are included in the models. You have the cooling feedbacks to the left and the warming feedbacks to the right. So you have the two big blue bars are the land carbon response to CO2 and the ocean carbon response to CO2. And these are essentially these things that I talked about in the beginning. The strength, how the Earth system is helping us by buffering the emission and taking volume up as a cooling feedback. But these are both feedbacks to CO2 itself. So it's the rising concentration, not the warming, that is driving these feedbacks. And that is quite important. When it comes to response to the actual warming, so land carbon and ocean carbon response to climate, that's actually a positive feedback that is warming the climate. So the warming is making it worse, the CO2 is making it better. Somehow, in this feedback specifically, but of course the CO2 is driving the warming itself. And if we take a look at this is a look at the global carbon cycle. This graph is slightly old now, but I still like it, so I keep using it. We don't need to get into the numbers per se, but this just shows the storage of fluxes of carbon in the Earth system, which is and its perturbations to this carbon cycle that we're talking about. And I just want to bring your attention that you can see it. You have these red numbers on the upper far left, which is for photosynthesis. It's 120, which is the big flux, and then +3. And the +3 in red, that is the added photosynthesis that is happening because of the CO2 fertilization from our emissions. So that is basically the cooling feedback where the climate is taking up more CO2 as photosynthesis because the plants grow better in a high CO2 environment. So if you breathe a lot of CO2 on your house plants, you should theoretically grow better. It's the same for nature. If you could go over and look at the ocean, you have the air-sea gas exchange there, and you have a number of 90 petagram +2 going into the ocean. That's the same. That's the oceans both being more productive, but also just dissolving more CO2 into the ocean because of the increase from our emissions. And then we have the part that we're really concerned about, which somehow ends up in the soil here, where you have microbial respiration and decomposition of soil carbon, which is the important process for permafrost feedback, where soil is thawing and then emitting carbon. So we had this graph where we showed the feedbacks that were in the models. Now this is from the same graph, another section of it, which shows the carbon cycle climate feedbacks that are not in the existing models in the recent reports. This is fire response to climate, permafrost response to climate, and wetland response to climate. So the IPCC acknowledges very well that all these feedbacks are missing, and they try to account for them in other ways in the report. Just note that taken together, this equals roughly 5 to 10% of the total human radiated forcing of 2.7 watts per square meter that we've seen so far. The bad news is, so they quantified the feedbacks. Even if they weren't in the models, they included it in the remaining emission budgets. That's also really good. The bad news is that the permafrost response is probably bigger than what it's quite a conservative estimate of the permafrost response, we have talked about this in earlier sessions, and we get into it here now, which has to do with abrupt processes not being fully included in their estimates. So the IPCC also looked at to what extent climate change is reversible. This also relates a lot to tipping points, and they ask this question: could climate change be reversed by moving carbon dioxide from the atmosphere? And they say yes, if it comes to global surface temperature change, but there will be lag times of several years. If you're looking at the permafrost extent, they also state that it's reversible, but with a lag time of decades, should perhaps be centuries. So this would point towards the not seeing at least a tipping point in permafrost extent under the scenarios we have here. They also identify other feedbacks that are not reversible. And this doesn't necessarily mean that they have tipping points, it just means that they act on very long timescales. In this case, we see the example of ocean thermal expansion that will keep going as a response to climate change regardless of what we do in the near term. And I want to get back to this one again. Now we're looking at permafrost area change again, and highlight that even if it might be reversible, the projection that the permafrost area might stabilize. It's stabilizing at a much lower level, which gives you an area of roughly 5 or 6 million square kilometers in this case that has thawed, that will keep emitting greenhouse gases for several centuries. Which means that the permafrost carbon feedback, regardless of whether we're talking about tipping points or not, is a very long-term committed emission source to the atmosphere, driven by our relatively near-term emissions. So this is an image illustrating this permafrost carbon feedback. I like this image because it has a massive scale to it. You have a person in front of the scale, which is actually a professor from the Building Institute who's standing there contemplating his surroundings. So the feedback system is that we saw the permafrost emitted greenhouse gases, and even more greenhouse gases are then released as organic matter is decayed and microbes consume it and release CO2 and methane. And the scale of this problem is related to the magnitude and the size of the carbon pool that's stored in the permafrost. The bubbles in this graph are proportional in size to the sizes of the carbon pools. You have the atmosphere, which is close to 900 gigatons of carbon at present. Permafrost is part of the global soil carbon pool, which is the biggest sort of responsive carbon pool in the Earth system. Permafrost is roughly half of that. It's estimated here at almost 1,600 gigatons of carbon in the permafrost region, with additional unaccounted deposits in very deep permafrost. So the scale of the problem, the size of the problem relates to this enormous carbon pool. In general, carbon cycling is rather slow at high latitudes compared to the tropics or semi-arid ecosystems, but the magnitude over a long time is immense because of this massive stored carbon storage and carbon pools. And now I want to bring the sort of discussion back to the tipping point. And here again I have this definition by McKay et al. Tipping points in the climate system occur when change in part of the climate system becomes one self-perpetuating to beyond a certain threshold, which leads to three substantial and widespread Earth system impacts. I'm going to try to look at this definition a little bit in the context of permafrost and what we know about that. So we have the feedback, permafrost thaw, methane and carbon dioxide release, more temperature. Then the question is then, is this self-perpetuating? We know that it's self-reinforcing, that's clear. But self-perpetuating would mean that all other things being equal, it would emit enough carbon to actually perpetuate itself. And then the second question is, do we have a threshold behavior in the permafrost carbon feedback? Are there specific temperatures where we will see thresholds that we need to be concerned about? The IPCC also asked this question. This is adapted from box 5.1 in that report. And they state it's unclear whether the permafrost carbon pool represents a coherent global tipping element of the Earth system with a single abrupt threshold, which would be the option, if we're thinking of this option, saying that the permafrost would be tipping at 4 degrees of global warming, as suggested by the figure that we saw. Or the other option would be B, 1 and 2 I should say. That permafrost is perhaps rather a local scale tipping point without abrupt thresholds when aggregated across the Permafrost region. And they also note that this is what is currently suggested by observations and global model results. So they favor the latter. A lot of local tipping points have not a coherent threshold at the global level. And I would, in general, the knowledge that we have supports that second statement. There is limited evidence for an Arctic or Pan-Arctic threshold tipping point in permafrost extent. This is one example of many that we can bring up to support this argument. But on the x-axis you see global warming at stabilization of different temperatures, and on the y-axis you see how much permafrost will remain. This is from a nice paper that came out years ago. And basically, if we would have expected, if there was a threshold behavior in this extent, it would look something like the orange line. But the green line is what we're really tracking. And what this means is that we don't see evidence of a specific threshold. But it also means that every single tenth of a degree matters. Every single tenth of a degree will damage permafrost. For every degree of global warming, we lose 4 million square kilometers. So I'm not saying that it's not extremely urgent. I'm just saying that there doesn't seem to be one particular threshold under which we are safe and beyond which we are doomed. So it's a slippery slope of a lot of loss, basically. And this is a graph from the special report on the climate and cryosphere, where we see basically the same thing. Predicted permafrost area change in either of these scenarios does not really appear to have any threshold behavior, and we do also see that you save a lot of permafrost under the lower emission scenarios, which also has long-term implications, limiting the emissions from the permafrost system itself. With that said, and as the IPCC also stated, we do see very extensive evidence of local scale tipping points in the permafrost system. And this at a local scale, when you lose the ground ice so the ice that is a big part of the permafrost system, and that melts and drains away as water, it is not going to reform on our timescales. Even if the climate stabilizes again, the ground ice does not reform. And abrupt thaw processes, so you see an example here, there's some people contemplating the upper corner of a massive ice wedge in the Siberian tundra in this case. This pure ice is in the soil, it's roughly 10 meters wide and 30 meters deep. And if you look at the whole volume of the ground, it's up between 50, 70, even 90% of the whole ground is made up of ice. So if that melts and drains away, the ground surface collapses. And over time, this gives you something like what you see on the right. The ice diminishes, the ground surface collapses. And even if you refreeze this ecosystem, the ice is not going to reform. So you will have, at least on human timescales, a permanent change to this ecosystem. And you see the photograph on the bottom right shows an example of abrupt thaw in a permafrost peatland that goes from an elevated dry surface to a low-lying wet surface after thaw. There are different types of abrupt thaw that have been sort of lumped together and upscaled in this paper from a couple of years ago now, which gives an overall view of the emissions associated with abrupt thaw landforms. You have hill slope failure, thaw lakes, and peatlands that so on will give you different trajectories of these local abrupt tipping points. And this is sort of trying to just summarize what happens over time. In this case, it's an example from a thawing permafrost. On the far left, you have stable permafrost, and that is usually a single CO2 and near neutral of methane in this case, if it's a peatland. And then as the permafrost starts to degrade, it will shift to usually being a sink, sort of a source of CO2, and in the case of peatlands, usually it can remain neutral when it comes to methane. But once you move into a phase where it actually thaws and it collapses, you have a post-thaw lake that is a strong source of methane and for a while also a strong source of CO2. Over time, if we had hundreds of years in this graph, you would actually see that it becomes a sink of CO2 again as the ecosystem becomes more productive. So these are dynamics that change over time. But on a time scale of a few hundred years, it will just lead to stronger radiative forcing and will be a source of warming. And this is just one example of how abrupt thaw can also be triggered quite rapidly. This is a paper that came out a few years ago now, but it shows how a few summer heat waves in the really far Canadian north, so in continuous permafrost, triggered quite massive abrupt thaw happening across the landscape in an area that wasn't supposed to thaw in another 70 years if you would have followed the model predictions for that area. So it's just how some extreme weather events can trigger abrupt thaw. So these tipping points can be triggered by weather, by fire, by other local events. And if you add this into projected emissions from thawing permafrost, here you see we have a graph that shows different degrees of global warming. The black dot shows what the IPCC projects with the gradual thaw. And if you add these abrupt tipping elements of abrupt thaw happening across the Arctic, we are looking at these purple dots instead, where you see almost a doubling of emissions from these systems. The units that you're seeing here should be gigatons of CO2 equivalents. I refer to that. So it's actually called CO2 and methane together on the y-axis. But so even though there's not a global or pan-Arctic tipping point in the extent of permafrost, these local tipping points matter a lot to the total carbon budget. Another thing that will also sort of make this even more dire is if you think of overshoot warming scenarios where we shoot past our target temperature instead of going directly to the target temperature as represented by the green line. Then our feedbacks from the permafrost will drive even further warming, as shown in the shaded areas. And the second problem is that a lot of this permafrost loss really is irreversible at human timescales and will keep emitting CO2 for several centuries. So if we add this into a similar graph of global warming, you see that overshooting the 1.5 degree target with half a degree or 1 degree gives a significant added CO2 emissions from the permafrost on top of no overshoot scenarios. So all of this taken together shows us that the permafrost carbon feedback eats up potentially a lot of the remaining carbon budgets to stable at 1.5 degrees, or the two degree budget. The full squares represent the full carbon budget, and then you see these hashed light blue areas that are going to be eaten up by the permafrost below. Now it's important to keep in mind the time scales that are relevant here, so that these permafrost emissions will happen they will start to really accelerate in the coming decades, and they will primarily happen at around 2100 or later, which means that this doesn't mean that rapid action would still limit us to. It doesn't mean that we are eating up sort of the window for rapid action of 1.5 carbon budget goal, but it means that those emissions will still come later, and they will be handled either they will add to the atmosphere again, or they will need to be taken back up with negative emission technologies in the future, depending on which vectors we follow. So, closing remark: permafrost co-emissions are a self-reinforcing global warming feedback for sure. At the global scale, we don't see a lot of evidence that permafrost co has any abrupt thresholds. Every 10th of a degree matters, but there's no clear abrupt threshold. On its own, permafrost emissions are unlikely to be self-perpetuating, in the sense that there is this potential compost bowl scenario whereby so much will be emitted that it will start driving itself. But that is extremely unlikely, I would say. I have not seen many papers supporting that hypothesis in a long time. But with that said, they do significantly exacerbate human emissions. We see abrupt creating local scale tipping points with irreversible impacts for several centuries. And we do see that permafrost reduces the remaining CO2 budget perhaps by half of 1.5 degree target in the most emission scenarios. And we important to note that once triggered, permafrost will cause emissions from centers. Okay, thank you for listening. I think we'll take questions later on. Or if there's a quick question now while we're changing slides. Okay, but then I think we'll move over to Brendan Rogers, who will give the next talk.
Thank you, Gustav. I do have slides too. Well, I'll start in the sake of time. So I'm going to investigate the question of whether we see evidence for tipping points in terms of wildfire in permafrost systems. And I think this is really important for a couple of reasons. It's important because the term tipping point gets thrown around a lot. It's important for the science because wildfire and these abrupt permafrost thaw processes are not included in models. It's important from the social dimension because if we do cross tipping points, what does that mean for our collective will to address climate action? And in the case of wildfire, it's very important because wildfire disproportionately affects both rural and indigenous communities in the Arctic. So I'm gonna, if you'll indulge me, take you on a little bit of an investigative exercise to ask the question, and I do get this question quite a lot, are we reaching, or is there a tipping point for wildfire in boreal forests and Arctic tundra? So I'm going to get into the weeds a little bit of fire science, but I think it's important to understand in the context of this question. For the sake of time, I'm actually going to skip the first couple slides because it's review, climate is warming, wildfires are intensifying, and they release lots of carbon that's not accounted for. I also had a glitch with this graph in my last presentation, so I know it's not going to work. And I want to get to the point of asking the question, what would a tipping point look like for wildfire in high latitudes? And I think from a scientific perspective, I start with looking for thresholds. Do we see threshold behavior, right? A threshold behavior can then become a tipping point depending on how acute that threshold is, how quickly we're crossing it. As Gustav mentioned, is it self-perpetuating? Is it reversible? And at what scale is it happening? Is it happening at a couple points, or is it happening at the continental scale to affect climate? Nope. That wasn't part of my slide there. Okay, here we go. So when I think about tipping points in the context of a wildfire, I can think about it in terms of burned area. Are we seeing more and more burned area crossing some threshold, resulting in a tipping point? Burned area, wildfires determined by both top-down controls, and I'll talk about this in a minute, but think about it in terms of meteorology, climate, but also bottom-up, so ecosystems, vegetation, soils, etc. But then we can also think about the tipping points in terms of the fire impacts on the system. So in terms of permafrost impacts, in terms of ecosystem impacts, are we reaching potential tipping points? I'm going to start with burn area and move towards the permafrost and ecosystem impacts. So what actually affects wildfire? What is driving wildfire in these permafrost regions? So the top-down controls that we think about are things like temperature and precipitation and humidity and wind, and these govern both the fuels that we call vegetation and soil, things that would burn fuel, so how dry are those fuels, but they also affect fire behavior. How likely is it to spread across the landscape? But also climate is affecting the length of the fire season, so just the amount of time we have for fires to burn. It's also affecting lightning emissions. With more energy in the atmosphere, we're seeing more lightning emissions. And on the bottom-up side, we think about things like biomass. How much biomass do we have to burn? What is the flammability of that vegetation? The structure of that vegetation, both vertically and horizontally. DUF, which is a fire science term for soil organic matter, fibric layers of the soil. How well drained the site is. That both governs how much below-ground fuel there is and how likely it is to dry out. And then at a larger scale, connectivity of the landscape. So we'll start with the bottom-down drivers. And this is a paper that came out recently, just looking at temperature, and I was really quite blown away. I knew that the Arctic was warming much faster than the rest of the planet, but I think these two graphs really highlight that in a way that I hadn't seen before. And so on the left, we see the time series of global temperature for the whole planet, but also the Arctic, and you can see the acceleration. And on the right, what they've done is calculated this Arctic amplification index, basically the ratio at which the Arctic is warming compared to the rest of the planet. So a ratio of 1 would be the same. And in the 70s and up to mid-80s, it actually was pretty similar, and you can kind of see that on the graph on the left. And then the 80s through most of the 90s, it was almost 3 times as fast. And in the 2000s, the ratio has been actually above 4. So right now, the Arctic is warming around 4 times as fast as the rest of the planet. So that, by itself, is an acceleration of one of the drivers of fires in these high latitudes. But we know that fires are driven not just by temperatures, they're also driven by, for example, precipitation. So I'm going to start with the tundra. This is a figure that was put together by Hu et al. In 2015, looking at the response of tundra fires in Alaska to these climate variables. So you have temperature and you have precipitation in the response of these tundra fires. And yeah, when I look at this, I actually do see threshold type behavior, right? If you sort of climb up from the green to the red in that 3-dimensional space, you are going up a slide that is steeper and steeper. So this is evidence to suggest that we are actually seeing some threshold behavior in terms of tundra wildfires in response to the climate. That was confirmed by this paper that came out last week in Science, looking at all fires north of the Arctic Circle in the last few years that has really been driven by Siberia. And these variables that I'm talking about, like temperature, precipitation, the two vapor pressure deficit and climate water deficit, there's ways of putting precipitation and temperature together that drive fire, length of the fire season, and number of ignitions. And in all of these cases, it's a nonlinear relationship, and I do actually see threshold behavior for the response of tundra fires north of the Arctic Circle to these conditions. Now, I would note that these exponential relationships are really driven by a couple fire years, 2019 and 2020 especially. So if we take those away, it's a little unclear what the relationship is, but nonetheless, that looks like threshold behavior to me. However, step back to note, most of the fires that are occurring across the permafrost region, across the Arctic boreal zone, are occurring in boreal forests. The vast majority are occurring in boreal forests. And if we look at that relationship, this is a little bit of an older paper, but I really like it because it has a bunch of the responses of boreal forest fires to climate. Here it's across all of Canada, on top temperature, on bottom climate moisture index, and at different scales, so going from about 100 square kilometers to hundreds of thousands of square kilometers. The main point I want to get across here is that this actually looks quite linear, especially if you look towards the right where it's clearer. The response of these boreal fires to these meteorological drivers looks quite linear, and that actually is pretty consistent with a lot of other papers out there. So my take on the situation for burned area driven by these top-down controls is that climate warming is accelerating. We are seeing threshold behavior in tundra regions that have not burned very frequently historically. They are crossing thresholds, they might burn a lot more. That might be a tipping point. But at broader scales, when we include the boreal, which is the vast majority of burned area, the relationships are likely a lot more linear. Now I'm going to talk about the bottom-up controls. So, you have these weather conditions and lightning conditions, but then the vegetation, the ecosystem really affects what happens for fire. So again, I'll start with tundra. There is some evidence informing this model that if you have low to moderate severity fires, the tundra systems are likely to be able to recover. But if you have high severity fires, you are changing the permafrost, you are changing the hydrology, and one thing that will happen is you'll get different types of vegetation coming in, like shrubs and even trees, and they tend to be a lot more flammable. So that, if that happens in tundra systems, could be a reinforcing feedback for more and more fires. I am not going to lead you through all of these diagrams, but this is another system that could have these self-reinforcing feedbacks. These are peatlands. So basically the model is in these peatlands, and there's a lot of peatlands in Canada and Western Russia, when they burn, well, if they dry from drainage or climate change, and then they burn, the fires tend to be higher severity. It changes properties of the soil, it changes properties of vegetation, you get more flammable species coming in. This could also be a self-perpetuating mechanism. And this is important because when we go back to these tundra fires that we've been seeing the last couple of years, this map on the left shows everything that burned between 2001 and 2018 in black north of the Arctic Circle, but then 2019 and 2020 is in red. So we had massive fires in the Siberian Arctic, and the graph on the map on the right is showing that a lot of these fires are occurring in peatlands. So if we are seeing threshold behavior in tundra regions, and especially in these peatlands, that can really matter for these systems. But I do have to say, the elephant in the room for these bottom-up feedbacks is what's happening in boreal forests. Again, because they are experiencing the majority of the burned area, and the story is quite different actually. So in boreal forests, especially those in Alaska and Canada, but also some in Russia, after we see fires, we often see deciduous, so these fires usually occur in coniferous forests, so spruce, fir, pine, but a lot of times you'll see increased levels of deciduous vegetation, deciduous shrubs and deciduous trees come into the ecosystem after fire. These deciduous trees are less flammable for sure. So this is a picture that I took in interior Alaska. It was a white spruce and aspen forest that burned, and you can see the understory, just 2 years after, is completely covered with aspen. So this will likely turn into an aspen forest, which is less flammable. So some work, for example, looking at this across all of Canada by Bernier et al. In 2015, looked at this avoidance or selection ratio of fire. Basically, are some ecosystems more likely to burn than others? And what they found is that, yes, the older forests, the coniferous forests, were more likely to burn, but the younger forests, the deciduous forests, were less likely to burn. There are some big questions. This is a negative feedback, so a dampening feedback. There are some questions about how this will play out with more warm, more extreme fire seasons. There's some anecdotes from fire managers that this model is no longer working, especially for late season fires, but nonetheless, it still represents a negative feedback, so that would sort of push the system in the other direction away from potential tipping points. So what is the net result that we see in terms of burned area? Well, we have the best data from across, we're missing a graph. Okay, well, there was a graph here. We had really good data from Alaska and Canada, and we've seen about a doubling of burned area, but there's nothing to suggest that it's anything but linear. So I would say for burned area across these large regions, we're not seeing We're not seeing an exponential increase. We're not seeing threshold behavior. Just the one on the right is because we don't have much data in Eurasia. So this is a recent assessment looking at fire emissions, but it largely follows burned area. And again, it's hard to draw conclusions from about a 20-year time series, but nonetheless, we're not seeing any kind of acceleration. There might be a linear increase in burned area. That said, that's across large scales. But I do want to just bring home the point that in the tundra regions, we are probably seeing some threshold behavior. This is looking at the Siberian Arctic, a long-term time series, and you can see the last couple of years, very far into the graph, have shot up quite dramatically, including the fires in these carbon-rich peatlands. When we look towards the future, I've shown this globe before, but this is just highlighting how quickly the Arctic is warming compared to the rest of the planet. It's represented by topography here, so these mountains. We don't know the exact climate trajectory because that largely depends on what we do as a function of these meetings at COP. But what we can do is look at how fires are expected to change as a function of temperature. And that is a pretty messy graph. These are different regions, different techniques. But again, there's nothing in here to suggest that it's a nonlinear relationship. It's a pretty messy relationship. So again, I would say at large scales, there's no evidence that we have threshold behavior or probably linear increases. That said, if you look at the axis, these are pretty big increases. So we're getting up to 2, 3, 4, even higher times fraction of burn area compared to historical. So it's important changes, it's big changes, but it's not necessarily accelerating threshold changes. All right, and then I want to end just spending a couple minutes thinking about the ecosystem or permafrost impacts when you do have a fire. Do we get some of these local tipping points? There are some cases where we certainly see resilient ecosystems. So this is a graph looking at the change in the active layer depth in permafrost after fires. You can see some increases after a fire. This is for tundra fires in Alaska, I believe. But by and large, over time, these systems are coming back to their pre-fire state. We do know that's not always the case. So this is some really nice modeling work done by Elfin Jafarov for black spruce forests in Alaska. And what you can see are these, so this is after a fire, year 0 would be a fire. In the upland system, if you have deeper and deeper burns, you can, in this model, get complete thaw of the permafrost column. In the lowland system, it's a bit more buffered and resilient, and so even the deeper burns don't necessarily result in complete thawing of the permafrost. And we do know, we have observational evidence that we can see some abrupt thaw after fire. So this would be very much a threshold change at that ecosystem at the time of a fire. So these are some pictures from Jones et al. 2015. This is the Anaktuvuk River fire, the north slope of Alaska, and you can see some braided detachment slides. You can see some retrogressive thaw slumps, and you can see some ice wedge degradation. So we have all kinds of abrupt thaw events occurring after this fire in ice-rich permafrost. And these are some photos from some work that I did in central Canada. This kind of gets to the other tipping point that Gustav showed with boreal forest dieback. I'm not going to talk a lot about that, but this is at the southern range of the boreal forest. On the picture on the left, what we have are these rapid rebirths. So we're seeing burning occurring more and more frequently. So this was about a 17-year-old jack pine forest that burned, and because of the repeated fires, it's burned completely down to bedrock. So I would love to go back there, but I severely doubt this is coming back as a forest. There's just not many places for the seeds to take hold. And there are cones in these trees, but we also sampled a lot of trees that were too young to even have cones, so they are not able to reproduce. On the picture on the right, this is one of those forests that isn't supposed to burn very much. This is a young deciduous forest. We saw a lot of burning. In the understory, you see lots of grasses coming up. So there are systems, especially at the southern end of the boreal, that if you see more fires, they're likely to transition to shrubs or grasslands because the trees just can't keep up with how rapidly the fires are coming. So, in conclusion, I would say that tundra regions display accelerating fire behavior related to climate thresholds. The relationships in a boreal certainly appear more linear, and again, that is the vast majority of burned area. I would say, similar to Gustav's conclusions, there's limiting evidence for one tipping point for all fires across the Arctic boreal zone, and in the language of tipping point, that's called a threshold-free feedback. We definitely see some ecosystems that are vulnerable to tipping points, so the ones I've identified: upland permafrost, moorland permafrost, permafrost with high ground ice, peatlands, and short interval reburns in boreal forests. but other systems certainly appear more resilient, especially lowlands, wetlands, and permafrost with low ground ice content. But I would say, even if we're not seeing threshold tipping point-like behavior, even a sort of linear or semi-linear increase of Arctic boreal fires with climate change has implications. This is a positive feedback. This means that if climate change follows more warming scenarios, we will see more emissions. So we're going to get more emissions from those fires with increased warming. And also that some of the lost carbon is irreplaceable on human timescales. But it also means that if we stabilize climate and eventually cool the planet, that fires are likely to follow. So that is my scientific conclusion of are there tipping points in fires in permafrost regions. Thank you. And we can take a question if there is. Yes.
You showed one chart where you showed one chart where the ratio between warming in the Arctic and generally was increasing. If you were to extrapolate into the future, what would you predict?
It's a great question. My sense is that it would be hard for it to go above the ratio of 4. Some of the feedbacks that we're seeing are very likely to continue, especially the loss of ground ice, and the fact that the Arctic has a lot more land. I don't have a great answer, but